In this last lecture in the module, we'll be talking about weather. To understand weather, we have to combine what we learned about in atmospheric circulation together with what we have been learning about with moisture in the atmosphere and also stability. And all these sorts of things start to come together in interesting ways. The first type of weather that I want to talk about are the types of storms that impact us in South Central Alaska and also much of the continental United States as well. In fact, large portions of both the northern and the southern hemisphere are regularly impacted by what are called mid-latitude cyclones or wave cyclones, they're also known as. They are formed along the polar front in the area of the subpolar lows. We've talked already about the subpolar lows. We've talked about the idea that it's a place where cold air comes from the north and meets warm air from the south. That air mixes together and lifts upwards. It lifts upwards particularly along that boundary as a result of some things that happen in the upper atmosphere that we're not going to spend a bunch of time talking about, but is ultimately related to the jet stream and to those Rossby waves that I mentioned before. What happens in the creation of these cyclones, or their cyclogenesis, is that low pressure forms along that boundary of cold and warm air. And as it does that, it starts to mix air masses. Cold air is brought in the northern hemisphere in a counterclockwise manner and is pushed into the warm air, forming a cold front. The warm air is also being pulled in counterclockwise, and it pushes its way towards the north, forming a warm front. This creates what is called the open portion of the mid-latitude cyclone, or the open stage, where we're getting this mixing of air taking place that we can see on this weather map right here. Cold front here, warm front here. Now you're going to have to spend some time looking in the text at pictures that show what's happening in this area. In particular, you'll want to learn a little bit about the clouds and the precipitation that form. Cold fronts are different from warm fronts. Cold fronts tend to have more cumulus clouds, warm fronts more stratus clouds, but it forms a great big sort of swirling comma shape of precipitation that's associated with one of these low pressure areas. These storms then track along with the jet stream, generally moving from the west to the east, though when they start to dissipate, they will actually start to break off of that. And it turns out in South Central Alaska, where we are, often we get the old storms. The young storms are forming out in the Aleutians and also in the very far Russian Far East. That's where there are new storms. That's where they tend to be open. By the time they get to South Central Alaska, they are often occluded. And what happens in the occluded stage of a wave cyclone is that all the warm air down here gets pushed upwards, and it's replaced effectively by cool air underneath it. The fronts are shown by purple lines that we'll take a look at in a little bit. The precipitation starts to slow down. The wind is not as great because the pressure gradient is not as strong generally as these storms start to lose some of their force. But they can still produce a lot of precipitation, as we know in South Central Alaska, where we will get snowstorms and rainstorms that are quite persistent that are created by these occluded wave cyclones. So again, take a look at the text and sort of get a feel for what these things look like. On a weather map, they are often a little bit more complicated than what we see in the textbook, but we can definitely find these forms. Here's a weather map that shows a relatively open and relatively new wave cyclone centered right over Iowa, it looks like. It's not a super strong low pressure area yet, but it's got a very distinct warm front and a cold front because that cold air is being pulled in counterclockwise from the north and the warm air counterclockwise from the south. Eventually, a storm like this we'll start to have a little bit of an occlusion, and this one you can see is a little bit stronger. There's a little bit more of tight lines around it, and you can see the purple occluded front right here with a cold front and a warm front here. This is still sort of an open stage, but moving into occlusion. This storm here, which is to the west of Alaska, this is Alaska right here, is a very strong storm. You can see the very tight isobar lines, which means that the pressure is changing very quickly as it moves towards that low pressure area. So the winds are very strong out in the Aleutians as this storm moves in, but you can see it's relatively completely occluded already. And that's because oftentimes these powerful storm systems in the North Atlantic become occluded out in the Aleutians. By the time they make their way into south central Alaska, they can still be relatively strong low pressure areas, but there is not this sort of distinct cold front, warm front that we see here. It'll be useful for you to take a look at pictures in the text that show this, but also to look at National Weather Service weather maps to actually see some of these things develop. Now, on a much smaller scale, thunderstorms are known as mesocyclones. They're still low pressure areas, so they are still air that is converging in the northern hemisphere counterclockwise. But in the case of a thunderstorm, it's a much smaller event, often caused as a result of atmospheric instability and convection taking place, though they often take place along cold fronts as well. When we get some sort of frontal lifting. In south central Alaska, we don't get many thunderstorms. When we do, it's almost always caused by instability and convection that often takes place in mountainous areas like the Talkeetnas and parts of the high Chugach. But in the continental United States, these things often take place in relatively warm areas, particularly in the early part of the summer or late spring, when we've got a lot of heating taking place in the ground and the air is still relatively cold, so the environmental lapse rate is quite steep, and that leads to instability. We get great big cumulus clouds that have precipitation associated with them, so they're known as cumulonimbus clouds. And they often have so much rotation in them because they're so intense that they create very violent winds both on the ground because of atmospheric pressure changes, but also within the clouds as well, which produces something called wind shear. That wind shear, air moving up and down within the cloud, forms hail and also lightning as well, because the particles of ice and water that are in the cloud statically charge the cloud, and those static charges are discharged as lightning. In their most severe manifestations, these mesocyclones can begin to spawn tornadoes, which are, of course, sort of the ultimate cyclone, very intense atmospheric pressure changes causing this swirling air mass that forms these exceptionally violent windstorms. Going back up to a bigger scale are tropical cyclones. Tropical cyclones, which we also know as hurricanes, especially in the Atlantic, and typhoons, especially in the Pacific, though they go by other names as well, are created as a result of low atmospheric pressure that forms in equatorial areas, so in the tropical areas, but generally speaking at the end of the summer, both in the northern hemisphere and in the southern hemisphere, when the low pressure is formed as far away from the equator as possible, so the Coriolis force has a lot of opportunity to impact it. They're created by the fact that you have very warm ocean temperatures at the end of the summer, because the ocean has been storing heat, and we know that oceans warm more slowly than land does, but also retain that heat. Small little waves of low pressure will come off the continents and start to feed on those warm ocean temperatures as sort of their energy source. And they will essentially, as low pressure areas, cause air to converge, again, counterclockwise in the northern hemisphere, clockwise in the southern hemisphere. And as the wind moves over the surface of the warm ocean, it will become very moist. It lifts up and cools adiabatically, And that releases a lot of energy as clouds form, and that deepens the low over time, causing increased convergence until eventually you start to get these incredibly powerful storms that have a great deal of structure to them. In fact, they have such low pressure in the middle of them that they often get what's called an eye of a tropical cyclone, because the wind is moving vertically much greater than horizontally, and it essentially blows out a relatively clear area in the middle of these storms with powerful walls towering around them. These are some pictures that show this. Again, you can see this in the textbook, but you can clearly see the swirling mass of air moving in the northern hemisphere counterclockwise. Here's what we can see if we sort of look at it three-dimensionally, with the air converging in and forming this eye in the middle. And then this is a cross-section of it showing the eye with the large rain bands around it. These storms are incredibly destructive. They have exceptionally high winds because the pressure gradient is so great between the air outside of the storm and the very low pressure at the center of the storm. They're also associated, as you can imagine, with a great deal of rain and the flooding that comes with that. But one of the most damaging aspects of a tropical cyclone is called the storm surge. The storm surge is caused by the very strong winds that are associated with the storm, but also by the fact that the atmospheric pressure is so low that the ocean usually rises, its tides are higher near the center of the storm. As we can see from the maps that I'm going to show you, or the map that I'm going to show you right here, is that they are formed in subtropical areas off of the equator, because remember, the equator doesn't have a lot of strong Coriolis force. So they're going to be formed at the end of the summertime in each of the hemispheres, and they will be tracked generally with the trade winds from the east to the west until they hit a land mass, and then they start to be picked up by the westerlies, and they start to move the opposite direction. This map right here shows the storms in terms of their intensity, with the greatest intensity being the reddish colors. And you can see that the greatest intensity tends to be as these storms develop over time, but before they hit land. Once they hit land, they run out of their energy source. And when that happens, they no longer are particularly powerful. And then the last type of weather that I want to talk about is actually, I think, what we would mostly consider to be non-weather, anticyclones, or high pressure. High pressure is still weather. High pressure means the air is descending, it is relatively dry, the skies are blue, there's no lifting, no precipitation taking place, but it is still a weather phenomenon that is associated either with the highs that are associated with the polar areas or with the subtropical areas that often move their way into mid-latitude areas as well. These are just a couple of pictures taken in the Denali area in the autumn when there was beautiful high pressure, and I happened to be in the area. You can see no clouds in the sky over here and very small amount right here. It's still a weather event, and it still impacts an area. And when you look at weather maps for Alaska, you'll often see high pressure areas or anticyclonic conditions. In the wintertime when that happens, it often means we have really long, dry, cold time because polar air is moving in. Sometimes in the summer, we're lucky enough to have anticyclones move in from the subtropical areas where we have relatively warm temperatures.